Okay, so in this lecture we'll cover what's known as constitutional or geometric isomers. So if we take several examples, so C2H6O for example. So I may ask you to draw as many possible molecules as you could draw. So C2H6O. So let's see, so carbon's got 4 valence electrons, times 2 is 8, hydrogen's got 1, 6 hydrogens, oxygen's got 6, so it's 12, 18. So the molecule should have 26 electrons. Okay, so if we drew some possible molecules, so we could attach the 2 carbons and then attach the oxygen. And then if we start filling in hydrogens, so this carbon at the end needs 3 hydrogens, this one in the middle would need 2. So to complete its octet, now it's got 4 bonds, and this one at the end now has 4 bonds, and so that's 5 hydrogens. You only have 1 to go, so you can put 1 on oxygen. That's 6 hydrogens. You've used all of your carbons, used all of your hydrogens. That's 1, 2, 3, 4, 5, 6, 7, 8 bonds, so that's 16 electrons. So you have, did I do this right? 1, 2, 3, 4, 5, 6, 7, 8. 16 electrons. What if I did wrong? Must have counted my electrons wrong. 12. 26. Okay, what am I doing wrong? 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8, 10, 12, 16. Okay, I counted electrons wrong somewhere. Oh, there's only 1 oxygen. There we go. So 8 plus 14, 20 electrons. That's better. Okay, so 8 bonds times 2, that's 16 electrons. We need 4 to go. And the oxygen will need 2 lone pairs to complete its octet, so then that would be 20 electrons total. Okay, so that would be one molecule that you could come up with, and that's a perfectly good organic molecule. Carbon's got 4 bonds, oxygen's got 2 bonds, 2 lone pairs, hydrogen's got 1 bond, everything is happy. But you could have drew this instead. You could have gone carbon, oxygen, carbon, and then this carbons would need 3 hydrogens to complete their octet, and oxygen 2 lone pairs, right? So again, oxygen typically likes to make 2 bonds and 2 lone pairs, 2 single bonds or 1 double bond. So again, that is C2H6O. So each carbon's got an octet, oxygen's got an octet, each hydrogen's got 1 bond. So that's 20 electrons, so that's a perfectly good organic molecule as well. So C2H6, you could have drew 2 different molecules. Both are reasonable molecules. Both molecules exist. So these molecules are what are known as isomers of each other. More specifically, they're called constitutional isomers, or sometimes they're called structural isomers. So same thing. So basically, constitutional structural isomers differ in the order of attachment of atoms. Right, the first molecule has CCO, for example. Second molecule has COC. So they differ in the order the atoms are attached, so they're constitutional isomers. Okay, if we take some other examples of constitutional isomers, so let's say we have C3H7Br. How many different molecules can you draw? So the easiest thing to do is, let's take the 3 carbons, attach them in the chain. So you have to keep in mind, carbon likes 4 bonds, hydrogen likes 1 bond, bromine likes how many bonds? It's got 7 valence electrons. It wants 1 more, so it wants to make 1 bond. So that'll help you not make mistakes, because if you put the bromine between two carbons, for example, you just made a mistake, because bromine doesn't like to have two bonds. It likes one bond. It's got 7 valence electrons. It wants 8, so it wants to share one electron and make one bond. So if you just keep the number of bonds that atoms like to make in mind, right? Oxygen 2, nitrogen 3, carbon 4, hydrogen 1, halogens 1, then that'll help you not make mistakes in the structures that you draw. Okay, so we attach the 3 carbons together, and then pick where you want to put the bromine. You could put the bromine at the end, that's fine, and then fill in with hydrogens. Carbon at the left needs 3, carbon in the middle needs 2, and then that carbon needs 2. That would be 7 hydrogens. Okay, so that's C3H7Br, so that's a good molecule. What if we did this instead? So what you want to recognize is that these are the same molecule. Right? It doesn't matter that we wrote the bromine on the left versus above the last carbon. The order of attachment of atoms is the same. It is still carbon, 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 bromine. Right? It's carbon, 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 bromine. Carbon, 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 bromine. Order of attachment is the same, so it is the same molecule. They're not constitutional isomers. But what we could have done differently is, instead of putting the bromine at the end, we could have put the bromine in the middle, on the middle carbon. And that would be a different order of attachment, because then it's carbon, carbon with a bromine, and then a carbon, so that's a different order of attachment. And then fill in the hydrogens. So that's C3H7Br, that's a different molecule. And then so just be logical about it, put the carbon on the right, then put it in the middle, and then what if you put it at the left? So if we put it at that carbon instead. And so what you want to recognize is that is not a new molecule. It is the same as this molecule, the first molecule that you draw, because it's carbon, 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 bromine. So the order of attachment is the same. It's just wrote backwards, but it's the same molecule. So for C3H7Br, only 2 molecules possible. Try as hard as you want, you will not come up with a different molecule, because there's not a different possibility. Okay, let's take one that's a little bit harder. How about C3H6O? Maybe, no, yeah, that's a good one. Okay, so let's draw. Let's draw as many molecules as possible. Okay, so again, let's take the 3 carbons, put them in sequence, and then let's put the oxygen at the end, and then let's fill in hydrogens. And then oxygen typically has 1, right? 2 lone pairs and 1. So if we did that, so then if we count our hydrogens, right, so carbon likes 4 bonds, oxygen likes 2 bonds and 2 lone pairs. So if we do that and then count our hydrogens, so we have 1, 2, 3, 4, 5, 6, 7, 8, which is 2 too many. So similar to counting electrons, if you count your hydrogens, and if you have too many, what does that mean? So that means you need to lose 2H so you need to lose 2 hydrogens and add another bond instead. So this is not a good structure because it's not C3H6O. This is C3H8O, and we want C3H6O. So let's get rid of two hydrogens and add a double bond instead. So get rid of two hydrogens between two atoms that are in a bond. That way when you remove those hydrogens, you can add another bond, and each atom maintains its octet. Okay, so that is C3H6O. So each carbon's got 4 bonds. Oxygen's got 2 bonds and 2 lone pairs, so it's got an octet. Each hydrogen has 1 bond, so that's a happy molecule. That's a good molecule. Okay, so now if you want to draw other possibilities, so what you could do is just slide the oxygen down. Instead of at the end, put it in the middle. So keep your carbon structure the same, and just put the double bond O in the middle instead. So that's a different molecule. So each carbon's got 4 bonds, oxygen's got 2, so everything's got an octet, hydrogen's got 2, that's a good molecule. So if we move the oxygen down another position and put the oxygen there, what you want to recognize is that is not a new molecule, that's the same as this. So that doesn't create a new molecule. So that's all that you can do by moving the oxygen atom around. So we need to try some other things. Well, you don't have to have a carbon-oxygen double bond. You can have a carbon-carbon double bond instead. So let's go back to our 3 carbons, stick oxygen at the end, but let's have a carbon-carbon double bond instead. And we could have put the carbon-carbon double bond there, or we could have put the carbon-carbon double bond there. 2 places, and that is 2 different molecules. And now we just want to fill in hydrogens. So this one needs 3, this one needs 1, this one needs 1, oxygen needs 1, and 2 lone pairs. So we could have done that, or the other molecule, this carbon needs 2, this one needs 1 to make 4 bonds, this one needs 2, oxygen needs 1. So those are both C3H6O. Okay, so now we have 4 molecules. Are we done? And the answer is no. So we could have had oxygen within the sequence. So we could have COCC, for example, or CCOC. But if we come up with one molecule that has a double bond, then as we'll see, then all of your molecules will have to have a double bond, or as we'll see, they could have a ring instead. So this molecule has to have a double bond. So if we put the double bond between the 2 carbons and then fill in hydrogens. So this carbon needs 2, this one needs 1, this one needs 3, and oxygen needs 2 lone pairs. Okay, so what about this possibility? What about the double bond between oxygen and carbon? And then if we fill in hydrogens, 1, 2, 3. So then that creates a problem, right? So this carbon at the end needs 3. This one would need 1 to complete its octet, and this one needs 3. But now you have 3, 6, 7 hydrogens, and you can't have 7 hydrogens. So that's not going to be possible. Okay, so with the oxygen in sequence, and that would be the only structure you could come up with. Okay, let's see in my, so you could have a ring instead. So carbon could have a 4-membered ring, and then these 2 carbons need, each carbon needs 2 hydrogens, so that's C3H6O. But it doesn't have to be a 4-membered ring. You could have a 3-membered ring. You could have an oxygen and 2 carbons in a ring, or you could have 3 carbons in a ring and oxygen attached to the ring. and then fill in hydrogens to give everything an octet. And 2 lone pairs on oxygen. Okay, so let's see. So that's all the rings you could have. 4-atom or 3-atom ring, and there's only 2 different 3-atom rings that you could create. One with 3 carbons and an oxygen attached, and one with 2 carbons and an oxygen and a carbon attached. And let's see, did I miss any? I think that may be all the structures. No. More structures are possible. So let's see, let's go back to this sequence. So we have the double bond there and oxygen here, right? Well, the oxygen doesn't have to be at the end. The oxygen could have been in the middle. Or if we go back and keep this sequence, so C and then C double bond C, the oxygen could be on the right, the middle, or the left. So we already had the one on the right. That's where we started at. So this won't be a new molecule, but this one will be a new molecule. Okay, so that's C3H6O. Each carbon's got 4 bonds. Oxygen's got 2 in them, 2 lone pairs. And this one, that carbon needs 2 hydrogens. This one needs 1. This one needs 2. Oxygen needs 1 and 2 lone pairs. Okay, I think that is all of the molecules. Except for this one we already have. That molecule is the same as where did we go? Same as that. Right? So this last molecule is not here. Okay, I think that's all of the molecules. So the point is, for very simple formula, all right, only 3 carbons, 6 hydrogens, 1 oxygen. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 different molecules. Unless I missed one, I don't think I missed any. I think that's just 9, but there's a lot of different possible molecules that you could come up with. So there's one thing that you can do that can help you. So there's no formula that I know of that will allow you to predict how many different molecules there are. So you just have to do trial and error. Just start drawing molecules and making sure you don't draw the same molecule. Keeping in mind, you could take a molecule and flip it over, and if it looks the same, then it's the same molecule. Or turn it upside down. If it looks the same, it's the same molecule. You just have to check the sequence of atoms and make sure the sequence is different. But there is a formula that you can use to help you when drawing molecules to know what kind of molecule to draw. So this CnH2n plus 2. So for our formula, C3H6O, so N is 3. And so then H could have been, so N is 3, then H, 2 times 3 plus 2 equals 8. So if you have 3 carbons, you could have put 8 hydrogens on the molecule, but you only had 6, so that tells you something. So the formula is this. So theoretical number of hydrogens minus actual number of hydrogens. So this is theoretical. Is 2n plus 2. The actual number is just whatever's in the formula, so C3H6O, and then divide by 2. So theoretical, 2 times n plus 2, so 2 times 3 plus 2 equals 8, minus actual is 6, divided by 2. equals 1. So this is what's called index of hydrogen deficiency, or sometimes called double bond equivalency, or sometimes called elements of unsaturation. So I usually use double bond equivalency when I talk about this. They're all the same. So 1 dBe, what does that mean? That means any molecule that you draw will have one double bond or one ring. So if you notice, every single structure that I drew for C3H6O either had a double bond in it or had a ring in it. Okay, what if you had two double bond equivalencies? So if we had a molecule like C2H2, so theoretical number of hydrogens, so 2n plus 2, so 2 times 2 plus 2, so 2 times 2 is 4 times, plus 2 is 8, minus the theoretical number, the actual number is just whatever in the formula, divided by 2, so 8 minus 2 is 6, whoa. Am I doing my math wrong? C2H2. 2 times 2 is 4, plus 2 is 6. Right, 2 times 2 is 4, plus 2 is 6, minus the actual number is 2. So 6 minus 2 is 4, divided by 2 is 2. So C2H2 has two double bond equivalencies. What does two double bond equivalencies mean? That means two double bonds, or two rings, or one double bond and one ring, or one triple bond. So they all count as two double bond equivalencies, or two index of hydrogen deficiencies. So as an example, if we drew a molecule C2H2, right, that's what you would come up with, triple bond. Obviously with only two atoms, you can't have two double bonds, you can't have two rings. So let me take another example. So let's more complicated molecule, C4H, so C4H4, is that going to be right? 4 times 2 plus 2 would equal 10. So let's make this 6. C4H6. So 10 theoretical minus 6 actual divided by 2. Two double bond equivalencies. Okay, so we could have had the 4 carbons. That's 1, 2, 3, 4 carbons. So then how many hydrogens does this have? This carbon needs 2. This one needs 2. And each of those need 1. 1, 2, 3, 4, 5, 6. So two double bond equivalencies is because two rings. Or we could have drawn that, right? 4 carbons, 2 double bonds. This needs 2 hydrogens, this needs 1, none. This one needs 1. This one needs 3. That's C4H6. And there's lots of possibilities you could have come up with. Right, you could have done that. The point is, this number, two double bond equivalencies, is information. It tells you whatever molecule you draw, Butter have 2 double bonds, 2 rings, could have 1 double bond, and 1 ring, or it could have a triple bond. Right, that's C4H6, C4H6. So all of these are C4H6. That's right. So this would have, those two would have 1 hydrogen, and this carbon would have 2, and this carbon would have 2. So they're all constitutional isomers. They're all structural isomers of each other. So if you know how many double bond equivalencies a molecule has, that helps you know what your molecule is going to look like. If you have 0 double bond equivalencies, then whatever molecule you draw better not have a ring, and it better not have a double bond, and it better not have a triple bond. And then beyond that, then coming up with the different numbers of molecules is just trial and error. Right? For this triple bond one, for example, the triple bond doesn't have to be at the end. Triple bond could have been in the middle. But we know there's a possibility of a triple bond, so then you just have to come up with all of the different possibilities. Okay. Yeah, so if we go back to this C2H6O, as you can see, we came up with 2 molecules. Neither one has a double bond, neither one has a ring, and the formula would have revealed this to you. C2H6O, so you just ignore oxygen when you do the formula. So 2N plus 2, so take that and plug in here. So 2 times 2 plus 2 is 6, minus the actual, minus 6, divided by 2 is 0. 0 double bond equivalencies, so whatever structure you draw for C2H6O better not have a double bond, better not have a ring in it. And so what if you have a halogen in the formula, like C3H7Br? So if we want to apply the formula C3H7Br, so if you have a halogen, so fluorine, chlorine, bromine, or iodine, then you treat it as a hydrogen for calculation purposes. So 3 times 2 plus 2, so 2n plus 2. So if n is 3, so 2 times 3 plus 2 is equal to 8. And then you treat the bromine like it was a hydrogen for calculating your number of actual hydrogens. So 8 minus 8 divided by 2 is 0 double bond equivalencies. And as you can see, for the C3H7Br that we came up with, right, no double bonds, no rings. And the formula tells you that. You got 0 double bond equivalencies, so you better not have any double bonds or rings in your molecule. So what if you have nitrogen in your formula? So C7H5N. So if you have a nitrogen, when you're calculating double bond equivalencies, take away 1 hydrogen from the actual number of hydrogens. Okay, so 2 times 7 plus 2 would equal 16. That's theoretical. Theoretical number of hydrogens minus actual is 4. So we're going to take 1 hydrogen away because of the nitrogen. So 16 minus 4 is 12, and then we're going to take that and divide it by 2. So whatever molecule this is, better have 6 double bond equivalencies in it. So there's lots of possible combinations to get to 6. So let me just show you that it works. So I'll just make up a molecule. Okay, let's see, that's 5. So that's 2, 3, 4, 5. How many carbons do I have here? 1, 2, 3, 4, 5, 6. We need another carbon. Okay, so that's 5, 6, 7 carbons. Got my nitrogen, 5 hydrogens. So this carbon triple bonded nitrogen doesn't need any. Let me just number these carbons: 1, 2, 3, 4, 5, 6, 7. So carbon 1 doesn't need any hydrogens. It's got 4 bonds. Carbon 2 has 4 bonds. Carbon 3 has 3 bonds showing, so it needs 1 bond, so 1 hydrogen. Carbon 4 needs 1 hydrogen. Carbon 5 needs 1 hydrogen. 6 has 4 bonds. 7 has 2 hydrogens. So that's 1, 2, 3, 4, 5 hydrogens and a nitrogen. How many double bond equivalencies does it have? Triple bond counts for 2. It's got 3 double bonds, and it's got a ring. So that's 6 double bond equivalencies, right? So of course, with that many atoms, we could have made a bunch of different molecules. I just using that to illustrate that the number 6 gives you information about the molecule. Whatever you draw better have 6 double bond equivalencies in it. Okay, so let me just make up a molecule and see if you can count how many double bond equivalencies it has. So let's see. Okay, so that's the molecule. So first of all, what's the formula? See if you can interpret the formula, the line formula, and then how many double bond equivalencies does it have? So you can pause the video for just a second if you wanted to and see if you can answer these 2 questions. So the formula is it's got 6 carbons in the ring, plus 1 there, plus 4 here, so 6, 10, 11. I see 11 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I see 12 hydrogens, and I see 3 oxygens. So how many double bond equivalencies? Well, there's 1, 2, 3, 4 actual double bonds, and there's 2 rings, so that should be 6. And let's see if that's what the formula gives. 11 times 2 plus 2 is equal to 24. That's theoretical. And then minus the actual is, we have 12 if I did my formula right. So that gives you 12, and if we take that and divide it by 2, we get 6, which is what I counted just visually by looking at the molecule, right? So the ring counts for 1, this ring counts for 1, and then double bond 3, double bond 4, double bond 5, and that double bond 6, 6 double bond equivalencies. Okay, we'll stop there.